In the last lecture, we have covered the Cauchy-Green circle theorem, and we mentioned what is the Cauchy-Green theorem and the meaning, of it. We gave a brief definition of the complex matrix and the deleted low sum and the Cauchy-Green disks. And the theorem said every eigenvalues of A rise within at least one of the Cauchy-Green disks. Proofs are directly followed from the definition of eigenvalue, eigenvectors with simple computations. So it shows the eigenvalue lambda is in the circle with the center as the ace of II and radius Ri. With it, we can say all the eigenvalues of A is in the union of all those Cauchy-Green disks and Cauchy-Green disks. Yes. And as a corollary, the eigenvalue of A must also lie within the Cauchy-Green disk Cj corresponding to the columns of A, because the eigenvalue of the set of eigenvalues of A is the same as the set of eigenvalues of A transpose, whose characteristic polynomials are same, because the determinant of lambda I minus A is same as the determinant of lambda I minus A transpose. Okay? So, we can think of lots of generalization of this theorem. Okay, now we start to explain the application of this Cauchy-Green theorem. As you saw, this theorem was used in the analysis of generalized Fibonacci sequence. Okay. Okay, this Cauchy-Green circle theorem is useful in solving matrix equations of the form AX is equal to B. Okay. Here, and particularly for such a system with a large condition number. Okay, condition number. Is there anyone who knows the condition number? Condition number. Yeah. Here is the definition of condition number in Wikipedia. So, in numerical analysis, a condition number is widely used. A problem with a low condition number is said to be well conditioned. And while the problem is a high condition number, said to be ill conditioned. Okay. For example, the condition number of A is equal to 10 to the kth power. Then you may lose up to k digits of accuracy on top of what would be lost to the numerical method due to the loss of precision from arithmetic method. Okay. So, how we can find these condition numbers? So, here we have seen the absolute value for the real number or complex numbers, and we also know about the norms for the vectors. With those definition of vector norm, we could define the matrix norms in this pattern, and then the condition number of matrix A can be defined in this way. And from this definition, we can draw the theorems like this. The condition number as the maximum eigenvalue of A over the minimum eigenvalue of A. So this is not only for the eigenvalues, it works also for the singular values as well. Okay, let me tell you more about singular values. So now we have defined the singular value of A from the normal system of AX equal B. So which means, so these are the square root of the eigenvalues of A transpose of A. Okay, so the maximum and minimums of singular values of A are defined in this way. From those, we were able to define the condition number of a given matrix A. Okay, if A is a normal, then kappa can be defined in this way. And if A is a unitary matrix, then the condition number A is equal to 1. Okay, unitary matrix. What is the definition of a unitary matrix? Okay, so lower triangular. So there are just, the consequences of those definitions. Anyway, so the singular values. Okay. So yeah, we have covered some background on condition numbers here. Okay, in this kind of problem, the error in a final result is usually of the same order of the magnitude as the error in the initial data multiplied by the condition number of A. Okay? Okay. Okay, so it would be good to reduce the condition number of A. This can be done. 조금 더 확대를 하면. It would be good to reduce the condition number of A. This can be done by preconditioning. A matrix P such that P is similar to A inverse is constructed. Then the equation PAX equal PB is solved for X. Using the exact inverse of A would be nice, but finding the inverse of matrix is generally very difficult. So, we thought this system of linear system of equations. Since PA is very close, similar to I, where PI is the identity matrix, so the eigenvalue of PA should all be very close to 1. So by the Gelshigoryn circle theorem, every eigenvalues of PA lie within a known area, and so we can form a rough estimation of how good our choice of P was. Okay, let me explain it by example. An example. Use the Gelshigoryn circle theorem to estimate the eigenvalue of this matrix. Starting with the low one, we take the element on the diagonal AI as the center for the disk, then take the remaining element in row and apply the formula to find the radius, deleted absolute low sum. Okay. Then we have the following four disks. For the first row, we have center 10 and radius 2. Here, for the second disk, center 10, radius 0.6. Here, center 2, radius 3. Here, center minus 11, radius 1 to 3. Like this. So we have four disks. We can have the four Gelshigoryn disks. So all the eigenvalues in the union of these four disks. Okay. Okay. Here, what this says is this. I'll explain it. Yeah. This for this example, this preconditioning process make the given linear system of equation as simple as possible by a similarity transformation. So having a more zero of diagonal entries is getting more closer and closer to the diagonal matrix or such a tri-diagonal matrix. So you can easily find the center of the disks and with the small radiuses. So you can easily designate the location of the eigenvalues. Okay. Here we apply this Gelshigoryn theorem to our Fibonacci sequence problems. So we can easily expect the area that all eigenvalues are located with the Gelshigoryn circle theorem. So we may take a look by simulation that how lambda behave as u getting bigger, changes, and how lambda behaves as v getting bigger and bigger. So you can see the simulation of it. So now, as for the generalized Fibonacci sequence of size 2 by 2, if this u moves from small one to bigger one, it shows how this is a Gelshigorian circle. So how this shows where the eigenvalues are located. So the eigenvalues are here, something like this. And so anyway, so this shows how we can use the theory to find the eigenvalues that tells us the ratio of those BIs converge. Okay. Anyway. Okay. Next subject is a Markov processor. Okay, Markov processor. What is the Markov processor? Okay, who can talk about Markov processor? Mr. Hong? Okay, Markov processor. Yeah, you must have heard about it. Yeah. Markov processor looks at a sequence of events and analyze the tendency of one event to be followed by another. Okay. A new sequence of random but related events which will look similar to the original. So it analyzes the situation that the new event will appear depend on the previous event. Markov process is useful for analyzing dependent random events. Okay. That is, events whose likelihood depends on what happened last. Okay, but it is not good matches to such a model like coin flip, 동전 던지기. It's not, because that coin flip game is independent event. It is not related. The one event is totally not related to the previous event. But many random events are affected by what happened before. Okay, yesterday's weather does not have an influence on what today's weather is. They are not independent. They are not independent event. They are even. They are related. Okay. Let's say it was found that 25% of the time a rainy day was followed by a sunny day, and 75% of the time rain was followed by more rain. Let's say we found out, or additionally, that sunny days were followed 50% of the time by rain and 50% by sun. Then given this analysis, we could generate a new sequence of statistically similar weather by following these steps. Okay? Okay. So, with these observations, with conditions, we may start to set up the model in this way, these steps. First, start with today's weather. Then, given today's weather, choose a random number to pick tomorrow's weather. Okay, the possibility, and make tomorrow's weather tomorrow's weather today's weather, and go back to step 2. So, move the come and go to expect the tomorrows. Okay, what we got is a sequence of days like sunny, sunny, rainy, 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 sunny, rainy, rainy. These are the simulation of from the model that we have discussed. Okay, okay. This stream of event is called the Markov chain. But taking a few events at a time, things feel familiar like this. Here you may listen the lecture that I have given on Markov chains. Can this address? 자, 5장 4절 마코프 체인과 리니어 모델. 마코프 체인은 과거와 현재가 상황에 왜 소리가 안 나지 또? 이 코덱을 아무래도 과거와 공격이 현재에만 드러난다는 그치? 성질을 이게 중에서 시간 공간과 상식. Okay, but so you will hear what 그렇다면 이때 what I talked about. And also, here's the information on the Markov processes, and that I may explain that. Here's the example of Markov process. Markov process was named for Russian mathematician Andrei Markov, and Markov property is the conditional on the present state of the system. Its future and past are independent. Markov process arise in probability and statistics in one of two ways: stochastic notice and Markov property. In modeling terms, assuming that the Markov property holds in one of the limited number of simple ways of introducing statistical dependence into a model for a stochastic process in such a way that allows the strength of dependence at different legs to decline as the leg increases. Here, there are, I think this is a good
Hello, my name is Jason Young, and I'm an undergraduate at Cardiff University, and today I'm going to give you a quick introduction to Markov
chain. It's a 2-minute lecture on Markov.
A Markov chain is a way of modeling a system, and the main properties of a Markov chain is that it has states and transitions. As we're looking at discrete Markov chains, the transitions are given by the probability of transitioning between two states. But there are also continuous time Markov chains that we will not be covering today. Here is the Markov chain for a student in a lecture. Here you can see our first state, arriving, is a
Since times are almost close, so I have uploaded this lecture note in iCampus, so you can just download it to go through it. And these lectures and also my lecture note covers the Markov property and some examples and the mathematical modeling related with it. And you may take a look what it is to understand it. And also I have uploaded the Korean version of this Markov process before, so you must be able to easily follow it. And even there is a song by the band Bad Religion. The title of the song is a Markovian process. You may also can hear the song Markovian process. The writer of this song is a doctor in biology.
Will say that I am surely crazy.
I hope you can enjoy it when you have times. And there are differences. And also, this Markov, you can find more information on Markov chains in Scientific American. And also, I found an interesting article on computer music, synthesis and composition and performance by Dodge and George. And here, Markov process technique was well used. And I heard this is a kind of classic on those the musicians who are using the mathematical theories in it. So you may some of who are working on those projects may have an interest on it. And I will continue the population models and this thing. But most important thing, in order to, as you have seen so far, in order to go through the mathematical modeling in theory and to the real applications, we need the mathematical background. So I'm thinking, for particularly, I'm trying to give more emphasis on linear models. So I'm next week from the next week, I may go through this the review part, or just one chapter of this matrix analysis textbook, the review part of it that has some informations like this, and this review part have only this. So So I will go through these review chapters, so at least you are familiar with the terminology and the theorems that I'm going to use throughout this course. Okay? Is there any questions? Then class dismissed. We will meet on Wednesday. You're supposed to upload what you like to share, and it will be those ones who got the comment by me, which has been approved to give to present. Then they will have a chance to show it. Okay. Okay. Good. Have a nice day.